like to introduce our speaker, Dr. Bart de Pontieu. He's a solar physicist whose research focuses on using high-resolution observations and numerical simulations to understand the physical processes that cause the rapid rise of temperatures from 10,000 degrees to millions of degrees in the low solar atmosphere. He's a fellow at Lockheed Martin's Solar and Astrophysics Laboratory, which is part of Lockheed's Advanced Technology Center in Palo Alto. Dr. Pontieu is also the PI, principal investigator for NASA's Interface Region Imaging Spectrograph, IRIS, a solar observing small explorer satellite mission built by Lockheed Martin, which has been observing the sun's atmosphere since its launch in 2013. He's also the principal investigator of the new multi-slit solar explorer MUSE mission, a solar observing medium class explorer satellite mission to be launched in a few years, hopefully. So Dr. Pontieu, without any more introduction here, we'll get started. Alan, if you could help me with the lights, that would be great. And let's do an audio check with you real quick.
Yeah, hi everyone.
Perfect.
Hope you can hear me. Okay,
sounds great. Yeah.
Well, thank you very much for inviting me. I really am very bummed that I can't be there in person. I've always enjoyed Chabot, and I've been an amateur astronomer myself. That's really how it all started for me when I lived in Belgium back many years ago now. And by some miracle, I was able to turn this into a professional career. And by some miracle, I've lasted in the soft money world for a very long time now. One of the things that you may be curious about is why I work at the Lockheed Martin Solar and Astrophysics Laboratory and why Lockheed Martin would be interested in solar physics. And I'll get to that in my talk. If I don't, please ask me a question at the end. The sun. When I was an amateur astronomer, I have to confess, I thought the solar physics or observing the sun was the most boring thing. And I've obviously changed my mind since then, and I'll get to that in a minute too. You can see here some data from the IRIS mission that captures a coronal mass ejection. It's this very large flow that you start seeing right about now, and you can see the Earth for size there. So you can see that we're quite insignificant. So in my talk, I'm going to talk about a lot of missions that the lab that I work at in Palo Alto has built for NASA. We're essentially a contractor for NASA. And over many decades, build up this laboratory with engineers and scientists that are focused on trying to understand the physics of the sun. So Solar Dynamics Observatory is one in the upper right. That one is probably very familiar to you. I'm sure you've seen data from it because anytime NASA publishes a story about anything related to the sun or even space science around Earth, it uses images from that. IRIS, we've already talked about, you can see in the lower left. And then there's also some data from the Hinode satellites, which is a Japanese JAXA space agency mission together with NASA and ESA contributions. I'm also going to show a little bit of data from the ground, from the Swedish Solar Telescope. They put a telescope in the Canary Islands because the weather in Sweden is not very favorable for observations of the sun. The Canary Islands are off the coast in Africa. So I know this is probably superfluous, given that you guys are all amateur astronomers, or most of you are. But I just want to explain a little bit what kind of types of lights we use to study the sun. We obviously, use the visible light quite extensively, mostly from the ground, because that light reaches the Earth's surface. And then a lot of our focus, and the focus that I'll have in this talk will be on the X-ray and ultraviolet light and extreme ultraviolet light. So that has higher energies, shorter wavelengths. You can see the scale of the wavelengths of the light here, atoms and molecules size. The reason why we use that type of light is because we can see the hot outer atmosphere of the sun. So I already mentioned that as an amateur astronomer, and I apologize to all the solar observers out there, I was not particularly intrigued by a flat disk with a few spots on it. And back in the days, when I was an amateur astronomer, we didn't have very large telescopes. It was mostly just counting spots and keeping track of, the solar activity, which, as we know, goes through a maximum every 11 years, and we're actually in a year of solar maximum activity. But of course, the story changes once you start looking with larger telescopes, and what we're seeing here is a blend really of solar dynamics observatory data for the full disk, going down to the very smallest scales that we can resolve with the Swedish Solar Telescope. And once you start doing that, it becomes actually quite fascinating. You can see cells that are surrounded by dark intergranular lanes. You can see some regions that are dark, and you can see some regions that are very bright that are kind of in these dark lanes. And once you start taking movies of it, and you can see the clock in the upper left, this is kind of an hour or so or two in the life of the sun. This is the surface of the sun, and it's what you're seeing here are boiling motions. This is what we call convection. We see convection cells form and then rapidly break up after about 5 to 10 minutes. They're about the size of California, each of these cells, 1,000 kilometers or so. What happens here is that energy that is generated at the core of the sun, I'll come back to that in a minute, is transported through mass motions in the last 30% of the way out, just below the surface of the sun. And just like on boiling, when you're boiling water, the water, of course, is a fluid. Here we're talking about gas. You have gases that become lighter and start to become buoyant and start to pop up to the surface, where they radiate their energy away, they cool off, and that's what they get transported to these dark lanes, and that's what causes this behavior that you see here. Now, the wrinkle here is very interesting. The wrinkle is that the sun's magnetic field also plays a role. Where the sun's magnetic field is very strong, it actually suppresses the convection, and that's where you get these dark pores, we call them. If they're larger, they become sunspots. But you also have smaller scale magnetic field lines, and that's all the crinkly, bright stuff that you see here. And as you can see, there's a real interaction going on here between these boiling motions and the sun's magnetic field. And as it turns out, that drives a lot of what we see in the sun's atmosphere. So here is data that we take with the Hinode satellite, this Japanese satellite, for which we built an instrument that measures the magnetic field. And the magnetic field here is shown. It's about a day in the life of the sun. Gray means there's very little magnetic field. Black means one polarity of strong magnetic field, and white is polarity of the is a strong magnetic field of the other polarity. And as you can see, the Earth is about the size of this orange, a little bit larger than this orange circle here. The sun's magnetic field is very different from the Earth's magnetic field. The Earth's magnetic field has a south pole and a north pole that is relatively stable. It changes over the course of hundreds or thousands of years. The sun's magnetic field changes on timescales of minutes. And there's a magnetic field that pops up from below the surface. It gets moved and sloshed around by these convective motions, and that's what all the dancing and jiggling is all about. And sometimes slams into each other. The opposite polarities slam into each other, and that's when a lot of action happens in the sun's atmosphere. So at the surface, the magnetic field is kind of the subject of the motions. The gas, the plasma, we call it, it's ionized gases, where electrons have been stripped from these atoms, and it starts to behave kind of like a fluid. We call it magnetohydrodynamics. So it's similar to a fluid, but it's got complications because the magnetic field also plays a role. At the surface, the plasma is in some sense stronger than the magnetic field and jostles things around, and the field has to do whatever it wants, whatever the gases want. As you go up to higher in the atmosphere, the density drops down, just like in the Earth's atmosphere. That's why climbers need oxygen masks when they go up to climb very high mountains like Mount Everest. And so the density drops down exponentially with height in the sun's atmosphere. The magnetic field doesn't drop down as fast and becomes stronger and starts to fill the whole, instead of being isolated in these narrow lanes, it starts to fill the whole atmosphere, and it kind of looks like a wine glass. Now, you all know that when you have wine glasses and you move them around and jostle them around, all kinds of interesting things can happen, such as breaking of the field, breaking of the glass, and fluid that goes everywhere. And in fact, that's really a good metaphor for what happens in the sun's atmosphere, and we'll come back to that later. So here's a movie that shows the Earth for size. You can see the Earth there, just above the limb, the edge of the sun. And we're now seeing the sun's hot atmosphere. It's about 1,000,000 degrees, and it starts to show indications of this magnetic field that these striations that you see. This is the ionized gas, the electrically charged gas that has to follow the direction of the magnetic field line, just as you would expect from Maxwell's laws. Now, one of the puzzles that we're trying to figure out is how does a solar atmosphere or stellar atmosphere work? And one of the key things to remember is that the energy is released at the core of the sun. That's a white region that you see here in this movie. That's where the pressures are so high that atoms get smashed together and fuse and release energy in the form of very high energy photons, gamma ray type photons. And those photons get absorbed, reabsorbed, re-emitted, reabsorbed, re-emitted, and they kind of do a random walk all the way out to about 70% of the way out. At that point, the gas is too opaque for this radiation to really effectively carry the energy out, and it becomes convectively unstable. And you start seeing convection cells. You start seeing energy transfer, not through radiation as much, but through mass motions. And in this is, of course, an animation. You can start seeing these bubbles as they pop up to the surface. And as they get to the surface, they emit their energy through radiation. That's why we see a nice sharp edge of the sun, even though it's a gas, it's not a solid object. And then the gas moves back down, cools off, becomes denser than the environment, and we get to a convective zone, which you can see here in yellow. So the core is in blue here. And then we have the radiative zone, we have the convection zone, and then we have the surface. Now at the surface, we call it also the photosphere. You get sunspots, and that's where the magnetic field is so strong it suppresses the convection. Just above the photosphere, and this is one of the big puzzles, is the chromosphere. And the chromosphere is hotter than the surface. The surface is about 10,000 degrees Fahrenheit. The chromosphere is about 20,000 degrees Fahrenheit. If you go even further out, you start seeing the corona. And that's where we'll see much better images of that in a minute, but that's these large-scale structures. They're millions of degrees. So it's very counterintuitive, right? I mean, if you have a candle and you have your hands very close to the candle, you're burning your fingers or your palms. As you move your hands away, things cool off, and that's exactly what happens in the sun's atmosphere. So here's a plot as a function of radius of the temperature. At the core, it's 15 million. Now we're talking kelvins. 15 million kelvins go down to 4,000 or 5,000 degrees at the surface, and then jumps back up in just a few thousand kilometers. And we've traveled already 695,000 kilometers when we go from the core to the surface. So this is counterintuitive. You can see it here as well. Here's the temperature. And the photosphere, where it's coldest, the chromosphere is hotter, and then the corona. Now, one key aspect of this is that the density of the atmosphere, as I said, drops down very precipitously over just 2,000 kilometers. This is what you'd expect from any atmosphere like the one on Earth as well. It's on average in hydrostatic equilibrium, and you get a certain scale height over which the density drops down. Now, if you don't have a whole lot of mass, it's easier to heat it. There's just a lot of mass packed in each cubic inch at the surface, and as that mass gets less dense, it's easier to heat it. So that's one part of this problem. But there's another aspect, and it has to do with the sun's magnetic field. And so let's talk a little bit about what this looks like in detail and see if we can gather any clues about what could be going on. Because what I showed you earlier is an average plot as a function of height. In reality, it's highly structured. We call it the coronal heating problem. It's been around for about 100 years, about as long as the dark matter problem. So it's a complex problem. We've studied it very extensively for the last few decades with space missions, and making a lot of progress. And I just want to give you a little bit of a few examples of the kinds of progress we've made in the last few years. So here's back to the boring sun that, teenage Bart was not particularly excited about. Fortunately, we have instrumentation now that can look at a variety of different wavelengths. And so this is an example of all the sun at one time, but observe the different wavelengths from the visible light through the ultraviolet light, which is the green and pink here, to the extreme ultraviolet light, which are these other colors. And so you see it's like a veil is lifted that shows you, how sunspots behave And we're looking really at almost a tomographical view of the sun's atmosphere. You see the sunspots that are sitting here at the surface, they're very cold, but in the atmosphere, they're actually very bright. And that actually often means that they're quite hot. And so we'll talk more about that in a minute. So let's walk back through this solar atmosphere. Here you can see the chromosphere. So this is about 1,000 kilometers higher than the surface. And you can now start seeing there's a lot more structure here. There's some regions that are quite bright. We call them active regions. And as it turns out, we can use the properties of the light to remotely diagnose and measure the sun's magnetic field. And the sun's magnetic field, so we use the Zeeman effect, and we use the polarization of the light for that. This is on board the Solar Dynamics Observatory with an instrument called HMI that was built in our lab. And it shows, again, the polarities of the strong magnetic field. And you can see their structure here. There's one active region here, there's another one here, there's another one here. And as it turns out, the heating of the atmosphere seems to be very localized to the regions where the sun's magnetic field is strong. So that gives us a pretty big clue that there's something going on related to the magnetic field. This is about 100,000 degrees. This is about 1,000,000 degrees. And here you start seeing very nicely striated and even loop-like structures. We call them coronal loops. They follow the direction of the local magnetic field. You can see some of them here too. You can even go to even hotter temperatures. This here gets to more than 10 million degrees. We're looking here at light emitted by ions. Iron ions, in this case, have been stripped about of 20 of their electrons. And so we know from laboratory experiments and from atomic physics that this equates to a certain temperature. Flares, which is what this is here, is an explosion in the sun's atmosphere that can drive up the temperature to even 100 million degrees. And a lot of interesting effects happen there. We'll talk a little bit more about them in a minute. The sun is not only very pretty in the extreme ultraviolet and ultraviolet light, but it's also very dynamic. And here's kind of a movie that shows some of the dynamic effects. So we're interested in understanding why this stuff is so hot. We see actually a planetary visitor here. This is actually a transit of Venus a couple of years ago. This is a multicolored movie. The temperatures, and it's a flare that you're seeing here. Here's a large eruption called a coronal mass ejection, where the magnetic field of the sun becomes unstable and ejects gases. You can see something similar here. It's not quite as successful. Much of the gas flows back down to the surface of the sun. What we often see in the sun's atmosphere and from these beautiful movies is that energy is released on very small scales, a couple of 100 miles or even less, but very rapidly reaches very large scales. I mean, this is about the diameter of the Earth. And so you see here, this covers in just a couple of minutes, tens of minutes at most, a very large region in the sun's atmosphere. Here's another eruption followed by almost kind of like burning prairie grass, front moving. That's a flare. And here you can see what we call post-flare loops that are formed in the aftermath of this restructuring of the sun's magnetic field. And here's another coronal mass ejection, almost gives the sun a giant ear. These are the kinds of events that we're quite interested in for reasons that I'll come back to in a minute. This is what we call coronal rain, where the heating process all of a sudden catastrophically fails and the gas starts cooling down and falling back to the surface. And here's another flare with strong magnetic field loops forming. These are sunspots tracked over several days. You can see there's a lot of motion in these. Again, these are regions where the field is so strong that the convection cells can't really be executed. You know, the magnetic field just constrains the motions of the gas of the magnetohydrodynamic fluid, really, so that the energy can't be transported efficiently from below. So why do we care about the sun, other than the fact that we're astronomers and we like to figure things out in the universe? There's another reason, and that is when a large coronal mass ejection erupts, it travels through interplanetary space and it hits the Earth, which is in this small box here. And when that happens, all kinds of effects can happen. They cause what we call space weather. The sun's magnetic field, the sun's particles have been ejected and magnetic field is being carried by these particles, can interact with the Earth's magnetic field, and the Earth's magnetic field can shield us from quite a few of these effects, but not always perfectly. You can see a little bit of that here. You can see some of these particles, we call them the solar wind. They're emitted continuously by the sun, even under quiescent conditions when there's no flares or space weather. But when a space weather event happens, that flux goes up enormously. And you can see some of these particles are deflected, and they're deflected by the invisible shield that we have, which is the Earth's magnetic field. It really helps us to be protected. You can see it here drawn with the North Pole in orange, and blue is the South Pole. Those particles follow Maxwell's laws. They're electrically charged. They have to follow the direction of the magnetic field. Now, of course, the ones that come straight down these field lines, they will hit the Earth at the poles. And when they do, we get beautiful things like this, northern lights. The northern lights are essentially when electrically charged particles have been accelerated by these storms on the sun, slam into the Earth's atmosphere, and hit atoms, nitrogen and oxygen atoms, and then give off nice, beautiful colors. By looking at these patterns, we can learn a lot about plasma physics, because this is all plasma, and there's a lot of interesting physical effects that we can study. Now, other than the beauty of northern lights and the physics that we can learn from studying northern lights, there's also the fact that we've become a very high-tech society over the last few decades. And this is actually one of the reasons that the Lockheed Martin Solar and Astrophysics Lab has been interested in this. Back in the 60s, when Lockheed was working for the Defense Department and building spy satellites, they realized, to look at the Soviet Union's activities, they realized that many of their satellites died for reasons they couldn't quite understand. And then they started realizing it had to do with the particles and fields in space, in near Earth space, where these satellites were flying. And as a result, they started realizing this is coming straight from the sun, many of them, and wanted to understand how to figure out how to protect their satellites better. And so space weather can cause issues with the functioning of satellites, as I mentioned, but it can also cause effects here on Earth. We have power grids that can be disrupted. In 1989, 6 million people in Quebec lost power for an extended period of time because of electric currents that are in space that can induce currents through Maxwell's laws on very large structures like transmission lines, and that can blow up transformers and lead to all kinds of problems. We have communication satellites that we use. We have radio signals that we use from space. Those all get disturbed when there's solar radio bursts. We have GPS that we use. Airline passengers, when they fly over the poles, especially people who work for airlines, may want to avoid the poles where the magnetic field of the Earth allows more of these effects to reach lower down. Satellites can be launched, and actually I'll come back to that in a minute. Astronauts are a major concern. Between Apollo 15 and 16, I think it was 16 and 17, I can't remember, there was actually a coronal mass ejection that if astronauts had been on their way to the moon, astronauts would have received a lethal dose of radiation. We got lucky. We didn't know about CMEs at the time, but we got very lucky at the time. So it behooves NASA certainly to figure out what the sources of space weather are, whether we can predict them, and whether we can mitigate some of these effects. Better predictions are key here, especially for astronauts, but even for commercial aspects of space flight. These days, there are many constellations that are being built. Starlink is probably the most well-known by Elon Musk's SpaceX mission company. And there are many, a couple of years ago, about 3.5 years ago now, actually just before I had a presentation at NASA headquarters about why they should fund our Muse mission. SpaceX lost 50 satellites in one day because they launched on the wrong day. They launched on the day when the sun gave off a flare, and that led to an increased density of the Earth's upper atmosphere, and it led to increased orbital drag. There's still a little bit of air up there, and satellites are subject to it. They plow into it all the time. That excess orbital drag meant that these satellites that had just been launched, these Starlink satellites that are illustrated here, decayed much more fast than they had anticipated. Many of these are brought into a low Earth orbit first before they get transitioned into a higher orbit. And so there was a very significant loss, and that's not the only loss that people have seen in the space industry. So hopefully I've convinced you that studying the sun is worth it, not just because it tells us about how it affects us, but also because we want to understand how a stellar atmosphere works, and the sun is the closest star and allows us to study detailed processes in such detail that we can take that knowledge and expand it to allow all these other physical processes work in the universe. The way we do that is we use the light. There are missions. There's a mission called the Parker Solar Probe that flies through the outer tips of the atmosphere, many solar radii away from the sun. That has led to very interesting insights. I'm not going to talk about that today. I'm going to focus here on how we do remote sensing. So we use the properties of the light. So you can see here, here's a spectrum. You can see the black lines. These are spectral lines that are emitted when electrons jump between different orbits. Different elements have different wavelengths and different energies. You can see the red to blue color here in the visible, but we have spectroscopy that we use throughout all wavelengths. And so spectroscopy is really what puts the physics in astrophysics. Images, such as the ones we've seen, are really amazing too, because they tell us how things are connected over large scales. But spectroscopy allows us to measure things like densities, temperatures, velocities, turbulent motions, and it turns out we really need that. How we measure velocities is really related to the Doppler effect, and I probably don't have to go into a lot of detail here. I'm sure you guys are all aware of the fact that as an observer sees a source of waves coming towards them, they will hear an increase in pitch, a shorter wavelength, and you can kind of see it illustrated here, and that leads to a blue shift. In the light is a wave phenomenon as well, and so it's not just sound, like an ambulance that you hear and the siren of the ambulance as it comes towards you go up in pitch and then go back down when it moves away from you. Light has the same properties, so we get blue shifted light when it moves towards us and red shifted light when it moves away from us. This is, of course, the way we figured out the expansion of the universe. So 12 years ago, we launched IRIS. This was a very long 10-second drop where you hope that the rocket actually takes off. This is from a chaser plane actually above the Monterey Bay. I arrived in the United States 2 days before this launch. I was a postdoc for the, sorry, not for this launch. I completely screwed that up. I'll blame COVID for this. I arrived, so this was in 2013, but I arrived in 1998, 2 days before we launched the TRACE satellite, which was a precursor of this mission, also with a Pegasus launch, and I saw it in the sky from the rooftop in Palo Alto. It was beautiful. So some of you probably have seen launches like this. I don't think the Pegasus rocket launches much anymore, but it was quite pretty to see at the time. So IRIS was launched in 2013. It was brought into orbit by the third stage that you can see here. You can see our torque rods that we use to stabilize. We use the Earth's magnetic field. We run currents through those torque rods and create torques to stabilize our satellites. You can see the telescope here. It's a pretty modest telescope. You can see star trackers here. Star trackers continuously are being used to maintain our altitude. This is before the deployment of the solar panels, which you now see opening here. And the beauty of something like IRIS, which has been running for 12 years, almost without interruption, is that it has no consumables on board. There's no fuel on board. So everything's stabilized using solar panels, the sun's energy, the Earth's magnetic field, and the electrical currents that we can drive through these torque rods, reaction wheels, and star trackers. And then here's the telescope. It has a door on it so that we don't get contamination. It observes in the ultraviolet light, and that's very sensitive to organics. So any kind of organic contamination could really screw up our throughput, how much light we get through. And so after about a month, we opened the door and then we started observing the sun. So this mission was a small explorer and has been looking at the sun's chromosphere and transition region, which is kind of the layers in between the corona and the surface for the last 12 years. Now, one of the things that it was very good at and still is very good at is it resolves very small details in the sun's atmosphere of about 200 miles. The movies I've shown you before are mostly from AIA, the Atmospheric Imaging Assembly on the Solar Dynamics Observatory, and that has a lower resolution. It can see the whole sun, but at lower resolution. IRIS looks more at a small region of the sun to look really at the details. And it's looking at the chromosphere in transition region because that's where most of the energy is deposited in the sun's atmosphere. The gas is much denser there, and it actually requires 10 times more energy to heat the chromosphere in transition region than the sun's corona. Now, IRIS is a spectrograph, and so it has a slit that it scans across the surface of the sun or the atmosphere of the sun, and then gets data like this. So this is actually data that shows the magnesium-2 spectral line in the near ultraviolet. It's not a line that we can see from the Earth because the Earth's ozone layer actually absorbs it. And what you can see here is as we walk in wavelength, Doppler shift, you can see here, through this line, we go and see very large changes in the morphology of the sun's atmosphere. This is, again, the chromosphere. This took us 24 hours. And you can see that we had to scan, we made a mosaic, and there's some gaps in there. That's what these little black lines are. The beauty, though, of this is that you can also measure velocities. You can see that in some locations, the sun's chromosphere shows gases moving towards us, often at supersonic speeds of tens of kilometers per second. And in other regions, the gas is moving away from us back to the surface at tens of kilometers per speed. So we've learned a lot about the dynamics of the sun's chromosphere this way and the role that shock waves play and other types of waves play in the sun's atmosphere. So I'm going to start with just a few pretty kind of movies. This one is kind of cool. It shows SDO, which is in the geostationary orbit, and it shows the Venus transit in 2016. The inset here is IRIS data. And the IRIS data, IRIS takes both images that you can see here, and then takes spectra where that black line is. And you can kind of see nicely that Venus moves up and down. And that's actually a parallax effect. So a viewing angle effect from the fact that IRIS rotates around the Earth in a very low Earth orbit continuously, whereas SDO, the Solar Dynamics Observatory that took this data, doesn't. And so you're seeing essentially the IRIS motion projected against the sun's background, which is kind of cool. Now, one of the things that IRIS was designed for was to figure out how the chromosphere works and what heats and drives the dynamics of the chromosphere. And it's done it's got lots of results. There's more than 700 referee publications now based on IRIS data. The movies that you see here, oops, there's supposed to be two movies, there we go, show again a tomographical scan through a spectral line, and the light at different wavelengths is formed at different heights. And so here we're in the photosphere. You see sunspots here, you see a light bridge. And then when you get to the chromosphere actually becomes bright above the sunspots. And this already tells you something about how the chromosphere is heated, and its heating has something to do with the magnetic field. You can also see a very significant change in the morphology. Here we're in the photosphere again with bright points that are where the gas motions concentrate the magnetic field. Here we're at the top of the chromosphere, and you see a lot more striations and loop-like structures that are related to the magnetic field. The chromosphere is very fascinating because it's a region of transitions. The gas is fully ionized, no neutral gases left at the surface. But in the chromosphere, because of the lower densities, you actually get more partial ionization. There's a lot of interesting plasma physics effects that happen in the chromosphere. And it's also a region where waves behave very differently than at the surface. One of the things that IRIS is unique for compared to ground-based telescopes is that we can observe the sun continuously for 8 months every year. We're in a sun-synchronous orbit where we only get eclipses by the Earth every winter, essentially, from November through February. But the rest of the year, we can observe the sun continuously. And here we see an active region, and we do really tomographical scans. So we scan across this region, and we get spectra in different spectral lines. It gives us access to different layers of the atmosphere. So we get space-time and wavelength, and it also gives us height. And so we see the photosphere, you see the upper photosphere, low chromosphere, and then the middle and upper chromosphere. And you see the evolution of the active region as it emerges from underneath the surface, where the sun's magnetic field is generated by a dynamo, and then the dynamic effects that occur from it. Now, one of the types of dynamic effects that we're very interested in is flares. These are large explosions where the sun's magnetic field is reconfigured, getting back to our wine glasses at the beginning, the sun's magnetic field is continuously jostled around and stretched by the convective motions at the surface, and that leads to tension. And magnetic field lines kind of behave a little bit like rubber bands. If you stretch them too much, they snap. Now, when they snap, when the magnetic field lines reconnect, we call it. It's called the magnetic reconnection process. It can lead to a lot of energy being dumped in gas. That leads to heating, like we see here. And it also can lead to waves being generated and acceleration of particles to very high energies, to relativistic energies. So electrons that are propagating almost at the speed of light. And it leads, when these electrons hit the surface, that's when you get these bright fronts moving. And these are what we call flare ribbons, and I'm sure you guys have seen some of that before. Now, with the iris data, what we get from the spectra is we see these are spectral lines here. So wavelength is on this x-axis for the two panels in the left here. We see the wiggling of the spectral line, and that tells us how fast the gas is moving towards or away from us. We see different spectral lines. This one's formed at 10,000 degrees. This one's formed at 100,000 degrees. And here's the image at the same time showing what the structures are that we're actually looking at. The slit is actually located right around here. And so we're seeing the spectra only along that slit. But we see in this case that we're catching the edge of one of the strongest flares in the last 10 years, an X8 class flare in 2017. It was the last one from the last solar cycle. We've caught hundreds of coronal mass ejections and eruptions like this. What the iris data allows us to do is to really study what's happening at the foot points of these regions, how fast does this gas get accelerated, and we do that with spectra like this. So we scan across, these are 4 locations on the sun. So we scan across the region as the sun evolves, and then we get spectral lines that are formed at different temperatures. And then we study, so we get the temperatures from this, we can look at the brightness that gives us some estimate of the density, and we get the wiggling of the lines that gives us the velocities, and the line width of the lines, how broad the lines are, tells us something about the turbulent motions in the gas. It turns out those are the things that you need to really pin down the physics. So let's talk a little bit about the physics. And let's talk about what are the likely mechanisms that heat the quiescent chromosphere and corona. So not the flares, but what happens in the typical atmosphere. So this is again the movie from the Swedish Solar Telescope showing the convection at the surface of the sun. There are really two, sorry, let me just go back to that. There are two major mechanisms that have been invoked. Alternating current mechanism, which is really based on magnetic waves. This was done by Alfvén, who postulated there would be magnetic waves in a plasma. And we'll talk more about those in a minute. And the idea is that these waves, it's a little bit similar to when you're boiling water, you can hear the bubbling of the water, sound waves are created. And so when you have convection, you get waves. When you have convection in the presence of magnetic fields, you get magnetic waves. And these magnetic waves are special because they can carry energy very far from the surface into the atmosphere. And one idea is that they propagate upwards along the magnetic field lines. You see the wiggly lines here, and then dump their energy in the corona. And that is one mechanism that could heat the corona. Another mechanism is happening on slower scales, DC. So you have AC and DC here. And in this case, you're moving more on time scales of the convective motions, which is 5 to 10 minutes. If you straightened out these magnetic loops that we've talked about, and you've got foot points here and foot points there, you make a straight set like this, and then you start moving these foot points around, like from these motions in the convection, pretty soon you get spaghetti. And the sun, the idea here is that the sun doesn't, the magnetic field doesn't like to be spaghetti, and at some point it will reconnect to go into a lower energy state. And when it does that, it can heat the atmosphere. So these are the two main theories. And so let's take a look at what we've learned from both of these theories. And one of the things we've learned is that we've had to move, and we've been fortunate to be able to move away from cartoons in the last 20 years because of supercomputing. So this here is not data from a telescope. This is data from a numerical model. This is a numerical model. It's a 3D box that we kind of a star in a box, so to say, the sun in a box, where we have a grid with thousands of grid points covering several Earth radii. This is about 2 or 3 Earth diameters, actually. And it's about 1 hour. And as you can see, and then what we do is we we put in all the physics equations, conservation of mass, momentum, energy, and some kind of equation of state into this numerical model. We seed it with some magnetic field, and then we let it evolve. And as it turns out, it can create its own convection zone, its own unstable cells that you see here. It even creates magnetic field lines that are concentrations that are concentrated in the downflowing regions, just like we see in the observations. So you could say, well, maybe we solved the problem. What does it do? Well, so these models are run on supercomputers. This is the Pleiades supercomputer of NASA Ames in Mountain View. And you probably have seen this before because it was in the Martian movie, which I'm sure you guys have all seen. I love this movie. There was one aspect of it that I wasn't in love with, which is that at some point the orbital dynamics person calculated the orbits to get the stranded astronaut back to Earth. And the way they did that is they took their laptop, plugged it into that supercomputer, and then after a while, it just said calculations correct. So this is how Hollywood thinks that science works. It's really not, of course. In reality, the models are never perfect. One of my colleagues once calculated we would have needed another 400 years of Moore's law to really get computers that would allow us to capture all the relevant spatial scales from the sub-millimeter or even micron scales all the way up to solar diameter to capture all the physical processes that we think may play a role. And so we have to make shortcuts when we make beautiful models like that. And so they're better than the cartoons. When I started my career in the 90s, in the previous millennium, it was mostly based on cartoons, right? And you looked at observations and you tried to kind of look at the cartoons and say, yeah, this could be what's going on. The computer models have changed the way we do physics and science, but we have to be very careful with the models. Just like with AI, there's some hallucinations in there. And so the way science now progresses is that you get these models that are advancing at a very rapid pace, not just through the hardware, but also through the algorithms. But you have to constrain them with the observations, and the observations have to keep pace as well. Some of these models can reproduce some of the observations, but often when you look at the details, you learn what's missing from the models, how you could correct them, and from that you gain physical insight. And so we've gone from this cartoon, and this kind of shows the idea of magnetic reconnection here, where you have field lines that are crossing, the spaghettified corona. When they cross, they come into this state here, and the magnetic field lines like to straighten themselves out. There's tension on these field lines. And when they do that, you get strong bidirectional flows away from that, what we call the current sheet. That's where currents occur. And so in the models, the question then is, okay, so we can create convection clearly in these computer models. Can we create a chromosphere and corona? And if we do, can we figure out what heats it? And can we solve the problem that way? And so, as I said, we start with seeding some magnetic field inspired by our observations, right? One polarity here, one polarity there. And then we've got magnetic field lines connecting. We can count. The beauty of these models is you can go and connect, go and investigate all the physics in this box without any complications, right? You actually have access to the physical variables in all these grid points. So you can calculate which field lines connect where. You can even calculate where the electrical currents are that were predicted in this braiding model, the DC mechanism, or the braiding of magnetic field lines, the spaghetti model. And then you can go and look, does it lead to heating? And as it turns out, you can go and study the evolution. You can see the magnetic field evolving here. Kind of, it almost looks like an observation. And here are the electrical currents that are predicted in the model. And you can see they happen all over the atmosphere, typically more in the lower atmosphere, where actually we know the heating is strongest, even though it's cooler because the gas is denser. But the dynamics of it are very fascinating. You can even go and observe from the side what the corona would look like. So this is now a prediction of what our solar dynamics observatory would have seen, and actually looks a lot like some of the data that we've seen. So it forms its own corona, millions of degrees. It forms its own chromosphere, tens of thousands of degrees, and it kind of looks like the corona and the chromosphere. The chromosphere is dark actually because it's cooler and it's absorbing that very energetic light. So you might think problem solved. Well, the devil's in the details, of course, and we haven't really figured this out fully, in part because IRIS is only designed to look at the cooler gases. It's not designed to look at the corona. And so one of the predictions that the models make is that these current sheets, these are currents showing above the surface of the sun. Here you can see a convection cell, and here in orange is the currents, should actually lead to heating in the same locations at the top of the chromosphere and in the very low corona. Now, it's happening on very small spatial scales that SDO cannot resolve, the Solar Dynamics Observer cannot resolve, but IRIS can resolve the chromosphere. And so when we look at the chromosphere, we can see actually what the density is in the gas by looking at the properties of the light. Purely based on an image like this, we can determine the density at various heights of the atmosphere. We use kind of tomographical technique for that and inversion techniques that actually use machine learning approaches to speed up the process by 6 orders of magnitude, 1,000,000 times faster than what we've been able to do in the past. That was an advance that was really driven by IRIS in the last 7 years. And so we can see these locations of higher density, that's where heating is strongest. And so one of the questions we have is, does that prediction from the model actually occur on the real sun? So we don't have a lot of data at the same high resolution of the corona as IRIS can see, because IRIS is blind to the corona. But we did have a sounding rocket a couple of years ago that observed for about 5 minutes. You can see the sounding rocket here, the high-C sounding rocket run by NASA Marshall, colleagues of ours, and I was a co-investigator on this mission. And we looked at the corona itself, at the low corona. You can see it's sometimes a little fuzzy, but it is higher resolution than SDO. And we could then go look at the heating patterns in the corona and in the chromosphere. We found a very good match. I'm not going to go into the details here, but it was very supportive of the idea that electrical currents from braiding are actually heating some of the strongest regions that are heated in the chromosphere and in the low corona. So that was a very nice advance. We also seen some other evidence for braiding, for this reconnection process. In particular from IRIS. Again, IRIS is blind to the black region, which is where the corona is, but in the cooler regions of the atmosphere, we actually saw, and you can see them here, the magnetic field line is in this direction, but we see very short-lived jets that are almost perpendicular to the magnetic field. They just last for a couple of tens of seconds. Now, this gas is only about 100,000 degrees hot, so not millions of degrees, but it's kind of like the smoking gun for coronal heating, we think, because we have numerical models that show what happens when fields interact. And what happens when the fields interact is that they will reconnect here in the middle, and they would lead to very strong motions perpendicular to the main direction of the field. And we think that what we call these nanojets might be driven by reconnection from braiding. What we don't know is if this is a process that was unique to that particular observation, or if it happens all over the corona. And we won't know that until we have an instrument that can measure these properties at the coronal temperatures, at the right temperatures. And you can see that process here. At time 0, the field lines cross, at 15 they still cross, and then at time 30 here, the field lines have straightened out and the gas has been accelerated in these directions here, perpendicular. So what about the other mechanism? Do we see any evidence for that one? And in the interest of time, I'm not going to go into a lot of details here, but the AC mechanism has also seen evidence. We have numerical models that predict that the magnetic field lines in the sun's atmosphere will shake because of these magnetic waves. These magnetic waves, we call them Alfvén waves after the Swedish scientist who came up with them from a theoretical point of view, have now been observed very ubiquitously, not only in computer models, but also in the atmosphere of the sun. They're similar to the kinds of waves that you get on a guitar string. They're driven by the tension in the magnetic field. So if you pluck a string on a guitar, the wave goes along the string and eventually then through the amplifier or whatever causes sound. But these waves are very efficient at transporting the energy that's generated in the convection zone through the chromosphere into the corona. So have we seen, here's another model of it. It's kind of a spaghettified model at very high frequencies, so higher, shorter time periods than the braiding. Have we seen them? Yes, we've seen them. This is from a paper that I wrote about almost 20 years ago now. It's embarrassing to say, that shows the kind of waving around of these fountains of gas that are continuously emitted by the sun's lower atmosphere. We call them spicules. And these are essentially caused by these magnetic waves. And there's a very strong flux of them. Now, the challenge is to figure out if they're actually getting dissipated too, if they actually can transport we know they can transport the energy, but can they actually also deposit the energy in the corona where it needs to happen? And that's We've seen indications for that, but again, at cooler temperatures that Iris is sensitive to, we really want to see them in the corona. And so for the corona, and I'll finish my talk very soon here, we are now working on a spectrograph that overcomes the limitations of our current instrumentation, that will look at the sun with multiple slits, called the Multi-Slit Solar Explorer. And you can see an animation here. We're building this thing right now in Palo Alto here. It's got 2 telescopes, and it's going to focus on the hotter parts of the atmosphere and and look at the sun, hopefully starting in 2027 for many years after that, hopefully. You can see another illustration. It's essentially based on the IRIS spacecraft. It's got the torque rod here too, got the solar panels, got star trackers, but it's got 2 telescopes that look not in the ultraviolet, but in the extreme ultraviolet light. So more energetic light, and that allows us to see the sun's corona better. You can see, again, these are telescopes that are quite modest in size. IRIS is an 8-inch telescope. And similarly here, these are about 8 to 10 inches tubes. Now, the beauty of the higher energy light that we're looking at, it has shorter wavelengths, and so the diffraction limit is much smaller at these shorter wavelengths. You know, these are wavelengths that we're looking at here of the order 100 to 300 angstroms, whereas visible light is at 5,000 angstroms. So to get, for example, the Swedish Solar Telescope is a 1-meter telescope that can resolve at 5,000 angstroms. It's a visible light, details as small as 0.1 arc seconds, about 70 kilometers or 50 miles or 40 miles. These telescopes here have wavelengths that are 50 times shorter, and so they don't need as large of a telescope to resolve small details. Now, one of the things that's very special about MUSE is it's going to address the fact that a lot of the physics in the solar atmosphere are fundamentally multi-scale physical processes. So it's going to use spectroscopy, which I've already indicated throughout my talk that that's what puts the physics in astrophysics. Images alone are not sufficient. But it also will do spectroscopy in a way that we've never done before. It's going to do it much faster than what we can do with IRIS. What you've seen in the IRIS movies is that we have a single slit along which we can do spectroscopy and have to scan it across a whole field of view. But that's often too slow to capture the dynamics of the solar atmosphere. And so we can't capture this coupling between very small scales on which coronal energy is released, and then very rapidly it spreads to very large scales, like in this giant eruption here. Typically, we would have a slit just here, and we wouldn't be able to see the velocities and turbulent motions and densities and temperatures that we want over the whole field of view at a cadence that is fast enough to capture the dynamics. So the kinds of data that we're going to get will look like this. So we're not going to look at the whole sun. We'll look at a good fraction of it, but focused on the size of about an active region. It's kind of it's a telescope. There are 2 telescopes, but they're kind of like a microscope in some sense compared to the Solar Dynamics Observatory. And we'll measure light in 2 passbands for our images that have a larger field of view at about 100,000 degrees, which is the transition region, and then the low corona. It's about 1 million to 1.5 million Kelvin. But along not just 1 slit, but 35 parallel slits will get spectroscopy. And we'll get 4 bright lines that allow us to cover a wide range of temperatures simultaneously. And that allows us to capture this multi-scale process that I've talked about. We'll measure intensities in these spectral lines, velocities through the Doppler shift, and the turbulent motions through the non-thermal broadening, the broadening of the spectral lines that is also caused by the Doppler shift. Now, one of the things that is really critical here is, and what's really unique about MUSE, is that we have these 35 slits. So on the left is a simulation of a solar flare. This is one of these fancy numerical simulations that I've talked about. It's what we call the ground truth here. In this case, of course, I have skepticism about some of these models because they have to make shortcuts, as we've discussed. But let's say that that's our ground truth. The challenge is that on the right is the data that we get at any one time from our best single slit spectrograph. And as you can see, the challenge is to make sense using the data on the right of what happens on the left. At any one time, these maps don't look anything like what's really happening on the sun. With MUSE, you actually don't have to scan across the whole scene. You only have to scan across the distance between neighboring slits, which is much smaller, and you can do that much faster, and that allows you to capture the dynamics of the solar atmosphere in a way we've never been able to capture before with a spectrograph. And so here's another example of it. In 12 seconds, MUSE will capture the evolution of this thing on the left very well, whereas the single slit spectrograph that still has yet to be built, because it's at very high resolution that we don't have, would only see a small little sliver like that. So MUSE will focus on coronal heating, like I said earlier, kind of really building on the iris advances to figure out, okay, are these processes that we see important in the corona? And how often do they occur in the corona? Because it could well be that both of these mechanisms play a role in different regions on the sun. And that's one of the key things that MUSE will do. Another thing that MUSE will do is we'll look at the drivers of space weather. So if we have an eruption here, or a flux slope, we call it, a magnetic field configuration that is unstable, that leads to a coronal mass ejection, we can actually go and measure the Doppler shifts, and we can see the velocities related to that coronal mass ejection as it takes off. And the hope, of course, is that by providing these new constraints on models of space weather that track the evolution of these events all the way to 1 astronomical unit, the Earth orbit, we can improve those models. And in particular, what we really like to know is, when will they arrive, right? When will they start wreaking havoc with our technology? So this is the kind of data that we hope to obtain. And for space weather studies, getting spectroscopy of this type will be quite exciting. A parallel activity that we do, and we use this extensively, is the development of different models. And these models are really cool, as I said. They look very pretty. The colors here are different temperatures. It's really a simulation of what this eruption would look like from the side with AIA. And it looks very similar to what we see with AIA. The problem is there's different models that make different predictions and different mechanisms involved. And to distinguish them, you really need spectroscopy. And we've shown that in a couple of papers and convinced NASA that with this kind of spectroscopy we'll do with MUSE, we'll be able to distinguish between the different mechanisms that destabilize the sun's atmosphere. And fundamentally, that leads to better physical insights of how space weather events are driven. Now, one of the reasons we're interested in this is because we know that the current activity that we see on the sun has impacts and economic impacts. There was a study done with a flare last year that happened in May that led to economic impacts in the Midwest in the agricultural sector, because, and I didn't realize this until I recently went to Congress to lobby for reversing the proposed budget cuts to the NASA science, is that I studied up a little bit, and several billions of dollars of economic losses occurred or were incurred because GPS was very inaccurate for several days because of a solar storm last year in May. And a lot of the agriculture now, the planting and harvesting, is done with tractors that are automated based on GPS. And if the GPS is not accurate, you can't drive those things, and it leads to a loss of crops. So that's just one example of how space weather affects us. The problem is that we know from the historical records, from the record in various forms, that super flares can happen. And this is an artist's illustration of a super flare. I think it might even be a movie. I don't think this is necessarily what it looks like, but this is an artist's impression of what a super flare would be. And a super flare would be like 10 to 100 times stronger than the current strongest flares that we've seen. Now, when a super flare would happen, we know that in the 19th century, there was the Carrington event that you may know of that led to daylight auroras in some locations. It led to folks that were handling the telegraph communications getting electrical shocks because electrical currents were induced on our telegraph network. Carrington events are larger, do occur. They're not very frequent, but what we call them super flares, they would lead to a loss of power for many, many months, and losses in the economy of trillions of dollars. So there is a reason to really study this, not just for ourselves, but also to understand the impact of stellar flares on exoplanets. We now know that there's thousands of exoplanets around other stars. And there's an active area of research where we try to understand what kind of space weather events on these flares can do to the atmospheres of exoplanets, and in particular, the habitability of exoplanets. And of course, that goes back to the fundamental question, are we alone in the universe? And so that's another reason to study the sun, because that's where you can really get into the physics of these mechanisms that drive space weather and the impacts of them. People are currently doing that already. They take our incomplete models of the solar atmosphere, extrapolate them to very different physical environments, and make predictions of what would happen to exoplanets. It really behooves us to figure out how the sun actually really works before we can extrapolate it to other stellar environments. And with that, I hope you guys are still there. And I think I'll stop here and be happy to answer questions. Thank you.
Great. Thank you so much. Get the lights. Thank you, Alan. What I'm going to do first is see if we have any questions online. And no Q&A online. Folks online, feel free to post some questions if you have any, and I'll get back to you. How about questions from the audience here? All right, Steve.
Thank you. Very interesting talk. Beautiful display of the data and explanation of what it's all about. Would it be correct for me to say that in the corona, which has a low density and therefore a longer mean free path, that these moving magnetic fields can accelerate the ions and particles there over a longer distance, thereby giving them a higher velocity, higher kinetic energy, and higher temperature?
Yes and no. I think you just came up with a theory that was proposed in the 90s that coronal heating is related to the mechanism that you described. We haven't seen evidence. We do see evidence for. Well, let me think about this for a sec and how to respond to this. It's a very good question. It's certainly true that in the corona you have low densities and you have a larger mean free path. We don't think that that's explaining everything that we see, but we do see evidence for some subset of gas being accelerated to very high energies that way, and we get non-Maxwellian distributions. And we actually used iris data for that to study. By looking at the spectral shape of the spectral lines, we can see that they have extended wings that would come from a mechanism like what you propose. And we do see some evidence for that, but it's not universal all around. One problem that you have is that in some regions, in many regions in the solar atmosphere, the density is extremely high, and well, not extremely high, not as high as in the chromosphere, but high enough to start disrupting some of the acceleration mechanisms. And so it's not settled yet whether that can really do all the heavy lifting what you propose. It's
so can I say
in fact,
that it's a partial explanation, but there's other mechanisms that I guess we don't understand.
I think the current consensus is that it's not the main mechanism, that this effect does seem to occur in some locations on the sun's atmosphere, but it doesn't explain the full coronal heating. That would be kind of my view.
Well,
but you could ask another solar physicist and get another answer on that.
Oh, hi. Thanks very much for the talk, and I appreciate you doing this while you feel sick. You're doing amazing. In some of your spectral stuff, you mentioned some elements that I wouldn't have expected could detect in the upper atmospheres of the sun. So you mentioned, I think, iron and also magnesium. Can you is that can you actually see those in the outer layers there like that? That's my question.
Yeah, no, it's a very good question. So most of the sun's atmosphere is, of course, hydrogen and helium. Much of the chromospheric light escapes to us. The chromosphere is optically thick. Let me start first with the chromosphere and then the corona. The chromosphere is optically thick, which means it's kind of like looking through a fog. A lot of the energy that comes out of the chromosphere and reaches us is through spectral lines that are hydrogen lines, the H-alpha line, which of course you guys are all very familiar with, and the Lyman alpha line in the UV. But there are trace elements that are actually playing a key role in the energetics in the chromosphere. And magnesium is one of the main ones. Calcium is another very strong contributor. And essentially the calcium lines and the magnesium lines, even though they're trace elements, because they occur at wavelengths where the sun is not so optically thick, can actually lead to a lot of the energy that we receive from the chromosphere because it's in the UV. In the corona, it's actually even a different story. In the corona, you really just have hydrogen is fully ionized and doesn't have any spectral lines. And this is one of the reasons why we have a hot corona, actually, is because most of the gas is hydrogen or helium. It's 90% hydrogen and 8% helium, and then the rest is 2% is trace elements. Because the hydrogen at some point gets stripped of its electron, once it does that, you get protons and they can't radiate energy away. And so that means that you're losing a cooling mechanism in some sense. And so that allows you to very quickly go up to very high temperatures until you hit a temperature where some of these trace elements can cool things down enough to keep the temperatures more reasonable. And so iron, as it turns out, has so many ionization stages, is one of the, has so many electrons flying around it that you can keep stripping away and you still have iron. And so iron actually plays a key role in the kind of energy household of the corona as a result. And yeah, I think I answered your question, but let me know if I didn't.
Yeah, thank you.
So most of the coronal emission, like this stuff here, that's most of what you see from SDO, from the Solar Dynamics Observatory, from this instrument here. These are the 4 telescopes. They're all looking at iron lines. And when we designed the AIA, we really looked at all these ionization stages. We wanted to cover a wide range of temperatures, and it's just the way nature helped us, atomic physics.
Okay. Anyone else in the room here? Nate?
This may be somewhat of an ignorant question. I mean, it is, but what goes on at the poles of this, the rotational poles of the sun? Is there less welling, or does it behave differently, or is it the same all the way around, essentially?
Very good question. It's an active area of research. We have instruments now. Most of our instruments have been in the ecliptic, orbiting Earth, and even if they're not orbiting Earth, they've been at the Lagrange point between the Earth and the Sun, and they don't go to very high latitudes. So we've not been able to observe the poles very well. But the Solar Orbiter mission that ESA is responsible for, that NASA also contributed to and launched, is being nudged to higher and higher latitudes through planetary flybys, and is starting to get its first views of the poles now. We noted that the poles during parts of the solar cycle, I didn't really talk a lot about the solar cycle here, but during parts of the solar cycle, you get very strong coronal holes. Coronal holes are regions that where the field lines connect to interplanetary space. Those are typically cooler. So the poles are often cooler, maybe only of the order of 1 million rather than several million of degrees. The rotation, the sun is not a solid object, so it doesn't rotate solidly. It actually has differential rotation. And so the sun rotates at a different rate at the poles than it does at the equator. And that actually leads to, we think has the side effect that it can create, it's related to the generation of the sun's magnetic field in the interior. There's also differential rotation as a function, not only of latitude, but also as a function of depth. And so studying the poles is actually critical for us to understand space weather, because a lot of the field, the magnetic field that makes it into interplanetary space originates from the poles. And the flux in the poles really determines kind of how far the fields reach and how they will affect us. In addition to that, this whole idea of the dynamo. One of the major unresolved problems in solar physics is how does a stellar dynamo, how's a solar dynamo work? How does a dynamo is a process that generates magnetic fields. We have one on Earth as well, or inside of the Earth, and that's has to do, we think, with the way flux collects at the poles during the solar cycle, how that flux sinks back down in the interior, how it gets migrated from the poles back to the equator. That whole process needs to be observed better, and so a polar mission is one of the key priorities that the National Academy of Sciences decadal survey, where every 10 years the community looks into what missions do we need to really understand the next big problem. A polar mission is one of our top priorities as a result.
Okay. Anyone else? Yeah.
For students interested in learning about the sun and space weather, is there a way for us to get involved in the research?
Yes.
Yes.
There's it depends a bit on which which where you are in your studies. There's the REU program, which is the research experience for undergraduates, that in the past has been funded by the National Science Foundation. The funding for that, of course, is quite uncertain these days because the president's budget request proposes very big budget cuts for these kinds of activities. We work together with the SETI Institute and do have interns or have had interns in the past. It'll depend on our budgetary situation, which we'll figure out in the next few months, where students can apply and work on research projects. We also have a long-running collaboration with the Palo Alto Unified School District, and we have high school students that come and work with us during the summer, and then also a couple of hours per week during the school year. We have, for Muse, we have an outreach program that actually involves Chabot as well, with the Galaxy Explorers activity at Chabot, and Becca Robinson, who is my lead for outreach, is working with Chabot right now to bring some of the Muse science to the Chabot Space and Science Center. So it's one of the reasons I'm really bummed I couldn't make it there in person, because I was looking forward to chatting with folks. So there are opportunities. I don't know which schools you're in right now, and I would suggest to send me an email. Again, as I said, I'm talking more about how things have been so far, but the NASA science budget is proposed to be cut by 50%. In the near future. So this is one of these activities that will be affected by that, obviously.
Okay. Anyone else? All right. Well, get some rest.
Thank you.
And don't be a stranger. Thank you for your talk tonight. And
thank you. It's been a pleasure. Thank you very much.
All right. Good night.
Thanks. Good night. Bye.